Hey guys, welcome back to chapter 14. In this chapter, we're going to look at some different definitions of acids and bases and start to dive in a little bit more how I know an acid is an acid or a base is a base. So in the world of acids and bases, there are multiple definitions for acids and bases. All of these definitions are valid, true, good. Some of them are a little bit restrictive, right? So as we move down the list, we get a little bit more inclusive and less restrictive in their definitions. So Arrhenius definition will be the first one that we talk about. It's a very simple definition, so that's kind of a plus side. It's a good place to start, but it also tends to be very restrictive. The next one is the Bronsted-Lowry. The Bronsted-Lowry definition is going to have a extreme focus on hydrogen. So where is that hydrogen going to and from? So it is a bit more inclusive. It does still have some restrictions to it. That being said, Bronsted-Lowry is kind of where we live in this chapter. And then the last definition is the Lewis definition. This is by far the most expansive. So what it focuses on is transfer of electrons. So everybody has an electron, right? So that's why it is the most inclusive definition. Is it, can track anybody during an acid-base reaction. So I'm not going to read all these, but here's just kind of a quick blurb out of your textbook about each of these definitions. Like I said, I'm going to spend some time in Arrhenius. I'm going to spend some time in Bronsted-Lowry. So Arrhenius definition defines acids and bases with respect to aqueous solutions. So there is your limitation, restriction. This has to be in water, okay? Not everything happens in water, but for those that do, we can use the Arrhenius definition. So an acid is defined as something that produces hydrogen ions when it is put into water. So if we put an acid into water, we'll see an increase in the number of hydrogen ions. Hydrochloric acid is our poster child for acid. So if I were to take hydrochloric acid, I were to drop it into a beaker of water, that hydrochloric acid would dissociate or break apart into its two ions. Its two ions that it breaks apart into are the hydrogen and the chlorine. So the chlorine's there. We don't really care about it when we're defining acids and bases. What we're focusing on is this hydrogen ion. So when it breaks apart, it dissociates. We do see an increase in the hydrogen ions. Bases, according to Arrhenius, are going to be something that produces or increases the hydroxide ion. So sodium hydroxide is our poster child. And what we see here is same thing. We drop sodium hydroxide into a water solution. It will dissociate or break apart into its ions. And it's going to break apart into sodium, ion, and hydroxide. Again, sodium's there. We don't really care about it. The hydroxide is what we're looking at. So that increase in the hydroxide is what classifies this as a base. While we're here talking about aqueous solutions, I want to note one thing that textbooks often do, but they don't really explain to you why they're doing it. So here we see this hydrochloric acid, right? So I told you hydrochloric acid will dissociate or break apart into its ions. If this hydrogen ion right here is formed in the presence of water, right? So if we pop off that hydrogen ion, it happens to happen in a water solution. That hydrogen ion is extremely reactive, very unstable, very reactive. So if it is in the presence of water, it will seek out a water molecule and form this complex that looks like this. So this hydrogen will attach to this water molecule to form this ion, and this ion is called hydronium. So the hydronium ion is a bit more stable than just a hydrogen ion by itself. Often chemists will use these two symbols synonymously. So they'll switch out hydrogen and hydronium. They'll switch out hydrogen and hydronium, and they won't like explain to you why or how they did it. They just kind of like swap it out, and they just assume that you know it. So I like to have this discussion here just to make sure that you guys are clear on what this H3O is. All right, talking about strength of acids and bases. What we looked at so far were two strong acid and a strong base. Okay. When we talk about the strength of an acid and base, we're going to use the same mindset that we talked about with electrolytes. Okay. So if I were to drop an electrolyte into solution, so what's an electrolyte? I'm so glad you asked. Remember, electrolytes are just simply ionic compounds that dissolve in water. Okay. So if I had something that was a strong electrolyte, I dropped it into water, that strong electrolyte would completely dissociate or break apart into its ions. Sodium chloride is a great example. For every molecule of sodium chloride that I put into water, it will dissociate or break apart into sodium ions and chlorine ions. None of them will stay together. Every single one will dissociate. If I jump to the other end of the continuum, we've got a non-electrolyte, so we put that in water, it doesn't dissociate. Not important. What is important is then this weak electrolyte. So non-electrolytes, we don't really talk about those in the acid-base world. That's why I said not important. So weak electrolyte, this is going to be something that partially dissociates in water. So maybe I put 3 molecules into water, and 2 of them will break apart, but 1 of them stays as that compound. It doesn't break apart. So we put all of them into solution, but only some of them dissociate or break apart. So that's a weak electrolyte. When we're talking about strength of acids and bases, it follows this exact same definition. So a strong acid or a strong base will completely dissociate in water, so completely break apart. Nothing will be stuck together. Weak acids and bases will only partially dissociate. So kind of the poster child for this is acetic acid, which we'll see in just a moment. But if we put acetic acid into solution, maybe 3 of them will break apart, but 2 of them will stay together. So only partial dissociation there. It's going to be important that we recognize weak versus strong, because as we start to solve problems with acids and bases, we're going to take 2 different paths to solving these problems. So if we recognize it as a strong acid or base, we'll take one path to solving. If we recognize it as a weak acid or base, that's a completely different path. So it's going to be important that we can identify the difference. So here is going to be kind of your first clue or indication as to what the difference would be. So this would be an example of a strong acid. So a strong acid is going to have a one-sided arrow. So for every molecule of this acid that I put in, every single one will dissociate into the hydrogen ion and then whatever the anion is. When we have a weak acid or a weak base, some of them will break apart into the forward reaction, so hydrogen ion and its anion. But some of it will stay together as a reactant. So we see this double-sided arrow. What does that indicate to you? Yep, those are going to be equilibrium situations. So when we recognize it as a weak acid, when we go to solve these problems, we'll have to use those equilibrium ice tables to solve this. So just a little preview, strong versus weak acids, and then we also gave you your Arrhenius definition. Hope you guys found this helpful.